Hello, I'm Devesh Shah and welcome to the video presentation of our paper titled Imitation and Supervised Learning of Compliance for Robotic Assembly. This is a joint work with my collaborators at Merle, Diego, Bill, and Daniel. Assembly is one of the key applications of robots, and thus robotic assembly has been studied since the last several decades in academic and industrial research. However, the problem remains open in several aspects and is particularly challenging for generalization to part location, which leads to uncertainty during contact formation. The main reason being that the vision algorithms cannot accurately provide the pose of the meeting parts, and the detection based insertion leads to complex contact formation, which makes insertion or assembly challenging. In this paper, we propose a machine learning based method for learning assembly using dynamic movement primitives, also known as DMPs, for moving the robot, and a supervised learning policy for performing local corrections during contact formation. We consider the problem of peg in hole assembly, where the hole location is detected using an industrial grade camera. The robot is provided a demonstration for performing insertion, and then the robot performs the insertion autonomously by learning a DMP and a force feedback controller to correct any contact formation. We test the proposed method using a physical robot hardware as shown in this picture. As we could see in this photo, our experimental setup has an RGB camera for hole detection and a force torque sensor mounted at the wrist of the robot for measuring contact force during any contact formation. Our main idea for the proposed work is to design a compliance controller for a position control robot by using force feedback in two different ways. First, we want to ensure that the contact forces are limited to safe values during any contact formation. Secondly, we use the force readings to learn a supervised machine learning model to correct the pose of the robot to perform insertion. We use vision information to estimate the initial location of the hole, and in general, the industrial vision systems are not accurate enough for tasks like robotic insertion. So here we show the design of our generalized accommodation controller that uses force feedback to change the reference trajectory. The reference trajectory is corrected by integrating force correction terms, and the proposed controller design ensures that the reference trajectory converges to some quasi-steady state, and thus the resulting contact forces also converge to some safe values. This figure shows the convergence of the contact wrench using the proposed accommodation controller for trajectories with constant velocity. The proposed controller guarantees the convergence of reference trajectories that have a constant velocity. This leads to convergence of contact forces during any insertion attempt. This ensures that the mating parts are safe during insertion attempts. This also allows us to use the steady state wrench vector to learn the machine learning model for predicting misalignment. During data collection for learning the supervised policy, we introduce a known misalignment in the radial direction and implement the reference trajectory using the proposed accommodation controller. Then we collect the steady state wrench vector as the force signature for the introduced misalignment. We use this data to learn a machine learning model between the force signature and the misalignment. Here we see the dependence of the steady state force signature as a function of misalignment. We can observe that there is a nonlinear dependence between the force signature and the misalignment. Consequently, we propose to use a machine learning model to learn this relationship. This figure shows the proposed architecture for our adaptive compliance controller, where the proposed accommodation controller is used to manipulate the reference trajectory. This controller is used for data collection. The data collected is used for learning a GP model for each of the X and the Y axis. During operation, this GP model is provided the converged force signature and it predicts the direction and the value of misalignment. This prediction is then used to perform local pose correction for the robot so that it can successfully perform insertion. Here we show regression and classification results for predicting misalignment using Gaussian processes. As we can see in the plot, the regression error increases with increase in the misalignment between the robot and the whole. However, the classification results are very reliable and we can get the direction of misalignment very accurately using this classifier. Consequently, we use the learned GPC model to predict the direction of error upon contact formation. Once the GPC model provides the direction of error, the robot is moved in the predicted direction and the steady state forces are read again if there is another contact formation. This process is repeated till the robot succeeds in insertion or it exceeds a maximum number of trials. You can also see this behavior of the robot in this video, and you can see that after a repeated number of trials, it is successfully able to insert the peg in the hole. This video shows our proposed assembly system. The robot is provided an initial demonstration for performing the insertion operation. This is used to learn a DMP for moving the robot. Now we collect some data by introducing the misalignment, as was explained in the process earlier, which is used to then learn a supervised learning policy to correct any misalignment. Now, during the actual movement of the robot, the whole location is detected by the camera, and then the robot is asked to perform insertion using the learned DMP and the supervised predictive model. And as you can see in this video, our method is able to generalize to different hole locations, and the robot is successfully able to sort of perform insertion by using the supervised predictive model. To conclude, robotic assembly requires generalization to part location, the initial location of the robot, and any contact formation during assembly. The state-of-the-art industrial vision system leads to imprecise localization of parts. Consequently, we propose a learning-based approach for robotic peg-in-hole assembly, where we propose a technique by combining DMPs with force feedback corrective controller. Using our proposed technique, we are able to achieve almost perfect insertion rates during the test trials.